In this paper, we present accelerating online reinforcement learning with offline datasets. How can we learn difficult tasks with little online fine-tuning by using prior datasets? Consider this door opening task. Prior data to solve the task may be available as off-policy data from expert demonstrations or from prior runs of RL. Prior work has considered offline RL, which maximizes expected returns using the prior dataset but without online interaction, and this may solve the task partially. But often, online fine-tuning is required to truly master the task. We will show that our algorithm can be used to solve these difficult dexterous manipulation tasks very sample efficiently. It solves this door opening task in under 1 hour of online interaction. We first study offline learning followed by online fine-tuning with existing methods. We find 3 shortcomings with existing algorithms in this setting on the half-cheetah v2 environment. The prior dataset we use is shown in the videos above, a mixture of 15 expert trajectories with 500 lower quality trajectories generated by behavior cloning. The first shortcoming is data efficiency. On-policy methods exhibit slow online improvement. Both AWR, which uses on-policy value estimation, and DAPG, which was used for fine-tuning from demonstration data, are relatively slow to improve online. Our method is superimposed to show how fast improvement could potentially be. Since we want fast online fine-tuning, we will focus on off-policy actor-critic methods. However, we find that actor-critic methods struggle in offline training, even if the policy is pre-trained with behavior cloning. Above, we see 3 examples of soft actor-critic. The blue curve is pre-trained on prior data, but we see it is no faster than the green curve, which trains from scratch. Even if SAC is pre-trained with behavior cloning, shown as the brown curve, the policy immediately deteriorates during online fine-tuning. Actor-critic methods can be stabilized for offline training by incorporating a policy constraint in the policy improvement step. The standard policy improvement objective maximizes estimated returns. Prior methods have investigated adding a constraint to stay close to the data distribution, which allows successful offline training with actor-critic methods. However, as we'll see next, prior methods have trained a behavior model, pi beta, by supervised learning, which poses a challenge in the online setting. Above, we see an example of BEAR, an offline method which enforces a constraint during the policy update, struggling to fine-tune online. When the constraint is loosened, the offline performance is worse, and fine-tuning is still relatively slow. The plot on the right shows the log likelihood of a behavior model which is pre-trained offline and then continuously trained online, split between offline and online data. We see that online training causes the behavior model to struggle to fit the offline data, and that the online data has even lower likelihood than the offline data. To address these challenges, we present our method, Advantage-Weighted Actor-Critic, or AWAKE. Our method incorporates a KL constraint into the actor-critic framework implicitly. This results in a policy update that resembles supervised learning. AWAKE trains well offline, fine-tunes quickly online, and does not require estimating a behavior model. We evaluate our method against prior methods on a suite of dexterous manipulation tasks. These tasks exhibit high action dimension, complex contact forces, and sparse rewards. For each task, we begin with a prior dataset of human demonstrations and off-policy data collected by behavior cloning on those demonstrations. As you can see, the behavior cloning is not very successful in many of these tasks. On this door opening task, we find that AWAKE begins at reasonable offline training performance and then learns quickly online. After 300,000 time steps, which is less than an hour of real-time experience, AWAKE has nearly mastered the task. Here we show the performance of prior methods on this task. Shown on the top right is the success rate after 300,000 time steps. Only AWAKE consistently solved the task. This object relocation task is especially challenging for prior methods to solve. We can see that after online fine-tuning, AWAKE successfully grasps the object and brings it to the target location marked in green. In comparison, no prior method makes significant progress on this task. This in-hand pen rotation task is relatively easier and can be learned to reasonable proficiency by offline pre-training. But we see that awake performs best after fine-tuning compared to the prior methods. We next evaluate our method on suboptimal prior data generated by a random process in a Sawyer manipulation environment. The random data is shown here, and note that the actions are independent of puck goal position, shown in red. We find that our method quickly learns the task from fine-tuning from suboptimal prior data. After 100,000 steps of online fine-tuning, it achieves a success rate of 90%. Finally, we evaluate our method for fine-tuning on standard Majorco benchmark tasks. Results can be found in the paper. Across these three tasks, we observe the same trends, that relative to awake, on-policy fine-tuning methods exhibit steady but slow improvement, actor-critic methods suffer from an initial performance dip, and policy constraint methods are too conservative when fine-tuning online.